Hi, today we are going to look at section 4.5, which deals with inverse relations. So with inverse relations, what we're essentially doing is reflecting our graph over the line y equals x. Now, when we do that, essentially our equation y equals f of x becomes equation x equals f of y. So essentially what that means is everywhere in our original equation that we had an x becomes a y, where we had a y in our original equation becomes an x. And as a result, our coordinates end up flipping. So if we have x comma y, it becomes y comma x. So if we had 1 comma 2, it becomes 2 comma 1. Now, one way that we note things are inverse is this f minus 1 of x. Okay, example, given the graph of y equals f of x, sketch the inverse. We're going to know if the inverse is a function and state the domain and range of each graph. Now I'll just do a small table of values for this. And it won't really be a true table of values. Instead, I'm just going to have my point on y equals f of x. And what that corresponding point is on x equals f of y. So we had -4, comma 4, -1, -1, 1 comma 3, and 3 comma 2. So if we take the inverse, this becomes 4, -4. This becomes -1, -1. This becomes 3 comma 1. This becomes 2 comma 3. So we'll plot these at 4. We are at -4. -1, we're at -1. 3, we're at 1. And then at 2, we're at 3. So if I graph that out, this would be our inverse function. Now, I'm just going to draw out the line of y equals x so you can see how it is essentially reflected over that line. That's our line y equals x. We can see our graph has been reflected over it. Now, we have the question of, is the inverse a function? So we have something known as a vertical line test. Theoretically, for something to be a function, anywhere on our graph, if we drew a vertical line, we should only pass through our graph or our line once. But if I draw a vertical line here, I would cross it twice, so definitely not a function. Or here I can cross it 3 times. Now state the domain and range of each. So for original, our domain, we went from -4 to +3. On our range, we went from -1 to +4. Now, if we look at our new graph, our domain went from -1 to +4. And we went from -4 to +3. So what you'll notice about the two domain and ranges is essentially the domain of our original function became the range of the second one, and the range of the first one became the domain of the second one. So as I just mentioned, the domain of y equals f of x is our range of x equals f of y. And the range of y equals f of x is the domain of x equals f of y. So next we'll look at determining the equation of the inverse function. So what we'll do when we're asked to come up with our equation, if they've given us the original one, is go through and replace the y in the original function with an x, and then take any of the original x variables and replace them with y's. We then rearrange to get y on its own. So determine the inverse equation of y equals x squared plus 4 and sketch both graphs is the inverse of function. So first thing, coming up with our inverse equation of this, I replace my y with an x, and I replace my x with a y. So I'd probably move this y squared to the other side to make it positive, move x to this side to get it away from our y. Take the square root of both sides. So y becomes the root of negative x plus 4. Now we'll sketch both graphs, both original and our new one. So we'll do a table of values. So I'll do x and y for our quadratic function, and then I'll just have our new coordinates in the last one. So for x values, I'm just choosing to go from -2 to +2. So -2 squared is 4. Plus 4 is 0. Then we've got -1 squared is 1. Plus 4 is that's 3. We've got 0 squared is 0. Plus 4 is 4. 1 squared is 1, but minus makes it negative. So that when we add the 4, we get 3. 2 squared is 4, becomes -4, so that gives us 0. So at -2, we're at 0. -1, we're at 3. 0, we're at 4. 1, we're at 3. 2, we're at 0. So our graph looks something like this. So I'll also label that, so that's y equals -x squared plus 4. Now we'll come up with our coordinates for our inverse. So for x equals f of y, we're at -2, 0, so it becomes 0, -2. -1, 3 becomes 3, -1. 0, 4 becomes 4, 0. 1, 3 becomes 3, 1. 2, 0 becomes 0, 2. So at 0, we're at -2. 3, we're at -1. 4, we're at 0. 3, we're at 1. 0, we're at 2. So our graph should look something like this. Now we can see this obviously does not pass a vertical line test, so it is not a function. Okay, so that's determining restrictions on the domain to create a function. So in some cases, we can make the inverse a function by restricting the domain on original function. So what we want to typically do is graph our original function and its inverse, and then find the sections that make it so that it's not a function, and figure out how to break original functions to eliminate those sections and create restrictions. So, example, determine 2 ways to restrict the domain of y equals x minus 1 squared plus 3 so that its inverse is a function. Okay, so for x values, I'm going from -2 to 4. So -2 minus 1 would be -3. -3 squared is 9, plus 3 is 12. Then I have -1. -1 minus 1 is -2. -2 squared is 4. 4 plus 3 is 7. Then we have 0 minus 1 is -1. -1 squared is 1, plus 3 is 4. Then we have 1 minus 1 is 0. 0 squared is 0, plus 3 is 3. Then we have 2 minus 1 is 1. 1 squared is 1, plus 3 is 4. Then we have 3 minus 1 is 2. 2 squared is 4, plus 3 is 7. Then we have 4 minus 1 is 3. 3 squared is 9, plus 3 is 12. So applying -2, I'm a bit off the grid at 12. -1, I am at 7. 0, I'm at 4. 1, I'm at 3. 2, we're at 4. 3, we're at 7. 4, we are at 12. So our original function looks something like this. So that's our y is equal to x minus 1 squared plus 3. Now our reciprocal, -2 comma 12 becomes 12 comma -2. -1, 7 becomes 7 -1. 0, 4 becomes 4 comma 0. 1, 3 becomes 3 comma 1. 2, 4 becomes 4 comma 2. 3 comma 7 becomes 7 comma 3. And 4 comma 12 becomes 12 comma 4. So at 12, we're at -2. 7, we're at -1. 4, we're at 0. 3, we're at 1. 4, we're at 2. 7, we're at 3. And then 12, we're at 4. So our inverse function is going to look something like this. So this does not pass a vertical line test. However, if I was to, for example, split this in half at a vertex and get rid of either the bottom part here or the top part here, we would then pass vertical line test. So if I go to my original function, I can put restrictions on this based off of that vertex. So we could say where x has to be equal or greater than 1, because that would mean that this section of our graph is the only section that we have, which would correspond to this section. So we'd then pass the vertical line test, or we can have x has to be equal or less than 1, which would mean that this would be the only part of our graph that we would have, which corresponds to this part, and we would once again pass the vertical line test.